in this passage, we're going to walk through the E2 reaction mechanism. That is the reaction mechanism for an elimination reaction. In other words, we will be eliminating two different groups from the starting material in order to yield an alkene product. And we're going to go through the steps required to get from the starting material all the way to the final product of this reaction. So let's take a look at the process, the pathway that the reaction goes. To start off with a starting material that's bonded to a leaving group, react with a base, and yield as our product an alkene. So we're looking at the E2 reaction mechanism for this process, where we will be taking as our starting material a molecule that is bonded to a leaving group as our organic reactant. So I'm just going to start here with this molecule. We're going to react it with NaOH, sodium hydroxide. And I'm going to give you the clue here that this is an E2 reaction mechanism, because keep in mind that the elimination reactions and substitution reactions compete with one another. And so what that means is that when you set up a mixture to do a reaction with that has something that could hypothetically act as either a nucleophile or a base, such as sodium hydroxide is capable of acting as a nucleophile or a base, you have the possibility of creating either the substitution product where the OH replaces the chlorine, or you can do an elimination reaction where the OH acts as a base, grabs a proton, and the leaving group leaves to create an alkene group in the final product. So we're focusing here on the clue being given that it's an elimination reaction. In actuality, if you were to do this reaction, you would likely end up with a mixture of products corresponding to an elimination reaction and a substitution reaction, and you could need to purify each of those two products in order to get what you desired out of the reaction mixture. Okay, so let's take a look at this E2 reaction mechanism. So the E2 reaction mechanism, the key features of that is it's going to involve the base grabbing a proton at the same time that the leaving group leaves. So the base removes a proton, and specifically it's going to remove a proton from the so-called beta position. And that's going to occur at the same time that the leaving group leaves. So it's going to occur at the same time that the leaving group is breaking away from the molecule. Much like with an SN2 reaction, the nucleophile was attacking the carbon atom at the same time the leaving group was breaking away. So when we say that the base is removing a proton from the beta position, we refer to the carbon that is bonded to the leaving group as being the alpha position, and the beta position is any carbon that is adjacent to that. So right here or right here. So the protons that we're referring to are any protons that are bonded at the beta position. So protons, or in other words, hydrogens, here, 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 here. And you'll notice that this molecule is symmetrical. So it doesn't matter which one of those protons we remove, we're going to end up yielding the same product one way or the other. So let's go ahead and drop down here and we'll write out the mechanism for this without quite so much scribble on everything. So I'm going to go ahead and plug in all of my different hydrogen atoms that are located here at the reaction site. This is a useful exercise to plug in these hydrogens that are present at the reaction site, because it makes sure that you aren't going over the octet rule for anyone, or that you aren't inadvertently leaving anything under the octet. So we'll go ahead and fill in all of our lone pairs and all of our hydrogens around the reaction location, just to kind of help with bookkeeping here of who's doing what and who's going where. So our oxygen is the atom that's going to act as the base. It's part of the OH minus anion here, because remember that's an ionic bond between sodium and hydroxide. So you'd also have Na plus floating around in solution, but that's just a spectator, so we usually pretty much ignore that. You don't even need to write that out, to be honest. So what's going to happen here is that the base is looking around, eager to form a bond to a proton. The proton it's going to pick is the proton right here, or any of these other 4 protons that are on the bottom here, 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 and here, because all of those protons that I put in green are all constituting beta protons, and removing any one of those four will end up giving us the same product in the end here. When that proton is removed, what's going to have to happen so that that hydrogen doesn't go over its allowed valence is this covalent bond between carbon and hydrogen has to go somewhere. It is going to come over to here to create the carbon-carbon double bond. And in order to avoid going over the octet rule, at this adjacent position, the alpha position, the leaving group has to break away so that we don't go over the octet on the carbon atom there. So as a result of this reaction, what's going to happen is we still, in our product, will have a carbon chain that has a total of 5 carbons. And I'm going to still fill in all my hydrogens just so that we're confident here that we haven't gone over the octet rule or under the octet rule for anyone. So right here at this position where I'm drawing in the hydrogen now, remember there's only one hydrogen there since one of them left. We come up here to where the chlorine was, and there's only one hydrogen there and no chlorine. And then our carbon-carbon double bond, our electron pushing arrow there, right here in the middle, showed that forming because our arrowhead ended up there between the two carbon atoms to show the formation of a carbon-carbon double bond. So we end up with the alkene product that we see here on the lower right corner. And we have indeed filled the octet for all of the atoms there. So we are good to go with this particular E2 reaction mechanism. The hallmark being that it's a one-step reaction mechanism where the leaving group leaves at the same time the base attacks. Much like with the SN2 reaction was also a one-step mechanism where the leaving group left at the same time the nucleophile attacked a carbon atom. So if we were looking at, for this particular reaction, the reaction coordinate, that diagram that shows us the reaction progress relative to the energy, so we'll put energy on the y-axis, reaction progress on the x-axis, what we would see is that our diagram here would have only one transition state because the reaction mechanism is a one-step mechanism. So we just have that one high energy state, that one transition state, and one activation energy in this pathway going from the energy at the beginning of the step to the highest energy point would give us our activation energy. And this is what we would expect for just a one-step reaction. So this energy curve that we've shown here looks identical to what it would for an SN2 type reaction. And here we're assuming that the reaction, by the way, is an exothermic reaction because the energy at the start, right here, is higher than the energy that I'm showing in blue at the end of the pathway, indicating that the reaction is exothermic. And we're just using exothermic as example here. All right, so with that, what we're going to do then is go into the next segment where we're going to look at the so-called Regio selectivity of elimination reactions. In other words, if there's multiple protons at the beta position where choosing which one you remove would give different products, different constitutional isomers, will there be a preference for one constitutional isomer over others? That's the notion of Regio selectivity, is the reaction chooses to make one constitutional isomer over other hypothetical possibilities. So in the next segment, we're going to look at how does the reaction choose which proton to preferentially remove, or is there a preference at all? So stay tuned for that in the next segment of this.